So this is the last one that we are going to cover, which is chapter 17E. That's a reaction mechanism. It can be very complicated, and what I want to even do anything, I want to emphasize the two things. One is steady state approximation. So this is very important for you to know. And then there's what is called the RDS. This is something that you probably heard it in the organic chemistry rate determining. You know, remember that? Determining step, right? So which is the slowest step when the series of reaction is happening, and this is what called RDS. And this has to be put it in part of it. The first one is elementary, like elementary school. Life is simple. Right? Elementary reactions. This is an easy reaction, and then we can think about it. And we've been dealing with this kind of experiment before. So if it is an A plus B goes to product, I guess the reaction rate is KR A. So that means if A and B collide each other, the concentration each component matters to determine the rate constant, and this is the rate reaction that you can see. But life is sometimes not that simple. Do you remember the complex reaction? And I'm going to write a couple of reactions right here. I can write this something. Sometimes a rate KA. I'm not even writing any further information than saying that this is an A. 2 K A K B A square B. Okay. Sometimes this is possible, right? And how come? That means this is not colliding each other to get the product. This one dissociate into something else, and that something else react with this, and they produce something else. So there's a more complicated cascade of reaction as given by Ka, Ka prime, Kb shown up here. And then you work it out. You even find out the rate law is more complicated. So what I'm trying to say here is, if somebody says that this is a elementary, you have to say that this one is elementary bimolecular process. I mean, somebody has to have this knowledge is that, oh, this reaction is elementary, and so it has to react this and to get the product. And these two molecules has collide, and in this case, I'm certain that I can write this one. And let me give you an example. Among this reaction that we write before, it is a radical, react with a bromine, and then we have a bromine substitution, and the bromine radical being produced. This is elementary. It's like a 2 billion volutes bouncing each other to get the new products out. And that one is I can say that's an elementary reaction that give rise, and then I can say B R square dt. This is a rate. It's minus KR H plus BR2. I can write this. This is not a question, okay? But do you remember that's H2 BR2 forming HBr. That was an example that I picked it on last class. And this one, this is a component to make up the whole net reaction that you see. This one is not as simple as this. Okay? So fundamentally, this reaction and this reaction is not the same. Okay? So that's what you, and essentially, here too, nobody knows. Okay? You have to do a lot of study to get the reaction rho constant, and why they are interested in studying the reaction rate as a function of these two concentrations and so on, because that's where the monies are. Okay, so that's why they did quite a study. Okay. Some of the one is very complicated, and this is we are just giving you a sample. So I guess we are picking on something that I can do it in a blackboard. When it's an elementary reaction, life is easy. Okay? When you're in elementary school, life was easy. I don't think that's true. But okay, so let's kind of start to getting geared up for a little bit more complicated reaction, and this is what is called a executive elementary reaction. So you're putting two elementary reaction in series. And then I can write, okay, A goes to product, but I'm going to put an intermediate. So there it goes to intermediate stages and goes to product. This can be a little twist from A to P right away. Okay? And then they put a Ka and Kb. Kb. And because it's an elementary reaction, so the first thing that you need to know is you need to learn how to write governing law. Okay? So I want to know how A is changing as a function of time. I want to know how I is being changed as a function of time. I want to know how product is changing as a function of time. This is the first thing that you should know. Okay? And probably this is the most complicated equation that ever put it into a GRE test if somebody want to go to that. So, okay, as far as this is just focusing yourself on one by one. Okay, looking at A, as far as A is concerned, this reaction rate doesn't matter. It's just only this one is the one that's taking away from A. So I can write now, this is decreasing Ka to the A. I mean, so far, so good, right? We've been doing this. So what about I? This is the one that is producing it, right? This is the one that is taking away. So all I need to do is I'm going to put it down. It's an elementary reaction, so I can assume it as a first order reaction. Okay? So this is Y. Okay? Even if it is not that, it will be even more complicated. But this is all first order. But by combining this kind of one, now this one is producing it, so plus Ka to the A minus Kb to the, anyone know what to put it here?
Concentration I.
That's it. Right? It starts to make sense, right? Yeah, so that's good. What about product P? I guess it is coming from here, right? So plus K B concentration of I. So what is the easiest one to solve it? This one. This one is easy, right? These two are not easy, right? And it is not easy. Okay, so what I need to do, and there are two ways to do it, and I want to show actually the one that I can do the math, and I will show you how to do the math. But this is an easy one. Okay, so we've been doing this. Oh yeah, this was A is a concentration of A naught, which is just a number exponential to minus KAT. I got that. Okay. So this is the one that I got. I can immediately write the correct answer. Taking this, plug that in. Okay, so what do you see here now? Concentration of I, differential to the T, concentration itself, and when you put this one there, Ka A naught concentration e to the minus KAT, which is just a function of a time, right? So if somebody write as dx dy plus y is 0. Do you remember this is pretty easy to solve? Separation of variable, so you put this one to the other side and go the other way. This is what we've been doing it. But now all of a sudden that this one is function of x. All I did is now is, let me change this one to p. Let me change this y into I. And then there's a sum, I guess something goes on underneath it, which is just a constant, which is a kb. Let me just simplify to a. So don't be deceived by this, how complicated it is. It is dx dy ay equal fx. This is an equation that you guys solved it before. Do you know what we remember what we call? This is a first order differential equation, non-homogeneous. Remember that? So to solve this, you need what is called the integration factor, which is this one to the e. So yeah. So this is the constant, so it's easy to solve it. It's an integrating factor, and you solve it, and you can do the whole thing. I just wanted to see that this is a y, this is a dx, dy, dx. The rest of them is a function of time. And you guys can do that. So by doing so, eventually you will get I as a function of time, right? Some kind of function of time. Let me just say that you guys can do. You can see my note, and I've spent quite a time to do it, to get it. But once you got this, what do? You plug it in. Right? You plug it in. You plug it in, and then so then the what? If this one goes to T, that's a P, so that's a separation of variable. It's another easy equation, right? So D product concentration is something function of time dt. And then it goes from 0 to t, it goes to p naught to p, which is just differences. And even this one is you don't have any product in the beginning, that's a 0. That's the one, this one on the left is just simply p minus 0, which is just a p. You guys can all do that, okay? And then if actually you don't have to do it. The solution is there, you guys can look at it. Just what is more important is I do not want to kind of dilute, instead of spending the time on here, let's just do this. Okay? And let's just approach this one in a different way. So I want to rewrite. This is what we can do, and then once again, this one is minus Ka to the A, and this one immediately I know A is A naught e to the minus Ka. That one I can just do right away. This is, we've been doing it. What about this one? Is once again, this is produced by A, dk of an A, and lost by KB. You guys can write this one down. This one is not complicated and it's very conceptually important. And then this is a KB. Okay, so that one is not so bad. And then I'm going to jump on to the what is called the steady state approximation, which makes I don't have to solve the differential equation in a big way. Okay. So I wanted to actually conceptually understand this one. Let me do this concentration versus time. So let's think about this is 0, this is the time, this is the concentration J divided by A naught. So concentration J means it can be A, it can be I, it can be product. I want to draw the three curves. Okay? So if I do this as a here, I start from 1, right? And then this one will be dk, right? Just the dk function. And this one follows, eventually if you go like this, that one is for sure. And then that equation is even well known as A naught or e to the minus KAT. The bigger the K value you will have, the sharper the drops is, the smaller they are, they have a much more longer changes and so on. But now, it's not even math. Let's think about the concept. So I write a Ka and Kb. Okay? Think about the car that moves from Albany to, let's say Montreal to Albany and Albany to New York City. Okay? Think about it. We are here in Montreal. This is Albany. And this is New York City. And if there's a lot of